Well, hello again and welcome to Math 315. This is the second recording in section 4. And we've been looking at these epsilon delta definitions of limits. And I wanted to go through carefully and do this example here based on the example we did before. So we're going to show from the definition that the limit of x squared as x goes to 3 is 9, which again is fairly obvious because 3 squared is 9, so the limit as x goes to 3 of x squared you would expect to be 9. We're going to prove this using the definition. Now, as I mentioned, these are probably the hardest bit we're going to look at. These are quite difficult, and you should be able to do at least questions like this one. So I'll go through one of these carefully, and you'll see that there's not that many steps involved in doing this, although it's conceptually hard. The actual writing out is not that bad. So I'm going to give an epsilon delta proof that this limit is 9. Again, I'll put my finger over what the delta is. We'll come back to that in a minute. So what do? We recite the mantra. Given epsilon bigger than 0, we put delta equal to, I'm not going to tell you yet. Then again, I look at the difference between x and 3, and I want that less than delta. That's always our opening line. And I want to look at the difference then between the function and its limit. That's x squared minus 9. So what do? We factorize this difference of 2 squares, so it's x minus 3, x plus 3, and I can split this up as we did in the earlier example. And we know the size of this one is less than delta, so I can toss that away and write this as less than delta times x plus 3. Now we have to do something about this x plus 3. And so again, I'm going to say if delta is less or equal to 1, then I can take this inequality here and I can expand it. So that's x minus 3 is bigger than 1, bigger than minus 1, less than 1. So again, I want to know what x plus 3 is, so I'm going to add 6 to both sides of this. So if I add 6 to both sides, I get x plus 3 is less than, add 6 to this gives me 7. So the absolute value of x plus 3 is less than 7. That means I can get rid of this thing now and say this is less than 7. So putting that together, that says the absolute value of x squared minus 9 is less than, this is the delta, and this is 7, so it's less than 7 delta. And I wanted that less or equal to epsilon, and that will be true if I take delta to be epsilon over 7. So what I do is, we did what we did before, we now take the minimum of whichever smallest, 1 or, from here, epsilon over 7 to get me my delta. And in either case, if I take the smaller of these two, as I explained last time, take the smaller of these two, then delta will be less than 1 and delta will be less than epsilon on 7. And so both of these inequalities hold. And I've satisfied the definition. Now that's quite difficult, and you might like to, well, we will try some more of these in the tutorials, just some simple ones, and that's about as far as I would expect you to be able to do. I'm going to show you just one more example of this, but this is probably getting to the point where I may not expect you to be able to reproduce something like this one, but I wanted to do one further harder example on this just to show you another aspect to it. So I'm going to show the limit as x goes to 1 of 2x squared plus 3x is 5, which again is obvious. You put x as 1 in, you get 2 plus 3 is 5, but we want to prove it using the epsilon delta definition. So hold this for the minute. So we recite the mantra, given epsilon bigger than 0, we suppose that x minus 1 is less than delta. That's always our opening line. We take x minus the point we're moving towards is less than delta. Then I'm going to look at the difference between the function and its limit. So that's 2x squared plus 3x minus 5. Now you'll see in the notes I've just blithely said this happens to equal this. Well, how did I get that? Well, I've got the calculations up here of what I've done. Firstly, I want to write everything in terms of x minus 1 so that I can use this. That's what I'm aiming to do. So I take my x, let me just take x squared firstly, and I want to write that in terms of x minus 1. So I'm going to write x minus 1 squared. Now, of course, that's not correct. But if I expand this out, I get x squared, but I also get minus 2x, so I'm going to add 2x, and I get plus 1 from here, so I'm going to subtract 1. So that now is a true statement. And now I'm going to come back and look at this, so I look at 2x squared plus 3x minus 5. Now the 2x squared is going to be 2 of these. I'm going to get plus 4x, 3x is 7x. I'm going to get minus 2 minus 5 is minus 7. And finally then, in this one here, I'm going to factor out the 7, and I get x minus 1. So all I'm doing is I'm rewriting this now as a polynomial, as a quadratic in powers of x minus 1, and that's what pops out. We can now use the triangle inequality, and we can say that's less or equal to twice this thing plus 7 times the absolute value of this one. But of course these are both deltas. So this is less or equal to 2 delta squared plus 7 delta. I've used the triangle inequality there. Now again, I'd like to combine these together, and I'm going to again say, well, if delta is less than 1, perhaps I should say less or equal to 1 there. If delta is less than 1, less or equal to, doesn't matter really, then delta squared is less than delta. You take a number that's positive but less than 1, then when you square it, it gets smaller. So a half squared is a quarter, and a quarter is less than a half. So I can replace the delta squared with just delta, and that gives me 9 delta. So, hence the difference will be less than epsilon. If I now choose delta to be the minimum of 1 to make this true, or from here, epsilon over 9. So this is less than epsilon if I take delta to be epsilon over 9. And that's, again, we've satisfied the definition. Now that one is very hard, and I don't think I'm going to expect you to be able to reproduce questions like that, but just to show you what happens in the most general case of this here. So, well, we'd like, as we did with when we looked at limits to infinity and so on, we'd like to get a sort of algebra of limits. We'd like an algebra of limits to enable us to find limits without resorting to the definition. We'd like to get some sort of algebra of limits to enable us to find limits without resorting to the definition. And that's given by the following theorem, 4.1. It just simply tells us if we know a couple of basic limits, then we can get more complicated limits of products, quotients, and sums. So if we've got a function f of x, if the limit as x goes to a of f of x is capital L, and the limit as x goes to a of g of x is capital M, then we can take and alpha and beta are any real numbers, then if we want the limit of alpha x plus beta times, alpha f of x plus beta times g of x, well, as you might expect, the limit's just alpha L plus beta M. Similarly, if I multiply the two functions together and then take the limit, as you'd expect, we just get the product of the limits here. And if we take the quotient of f, we divide f of x by g of x, we'd expect in the limit we get L over M, well, provided we're not dividing by 0. Now the proofs of these I'm not going to go through. They're very similar to the proofs of theorem 2.2 that we did back in chapter 2. Now we'd like a version also of the pinching theorem that we had for limits of sequences. We'd like to have a similar pinching theorem for limits of functions, and that's provided by this theorem 4.2. So we've got three functions, f, g and h, defined on the same interval I, so that the f is squeezed between g and h. And that's for all x in this interval, and we take a point A inside the interval. Then this says if the limit as x goes to a of g of x and h of x, if they both have the same limit L, then because f is trapped between them, then this limit is going to exist and equals L. So we can draw a little bit of a picture here with this. So what have we got? We've got g's the smallest. We've got h is the biggest, and we've got f is trapped somewhere in between, so there's the point A. So this was the h up here, this was the g down here, this is the f there. Then you can see geometrically that if g has a limit as we go to A and h has the same limit as we go to A, then if we go along f, then that limit has to exist, and it's going to equal the limit L here, which is the common limit of the two other functions. Now this theorem also holds for limits of functions as we go to infinity. This here A was a finite point, but it also works for limits to infinity. And I want to do just a simple example of this. I'm going to use the pinching theorem to find the limit as x goes to infinity of sine x on x. We've done ones a bit like this before when we did limits of sequences. This is just much the same thing, but here's the calculations for this. So we're going to do the limit as x goes to infinity sine x on x. And we expect that this is going to be 0, because if x gets very big, sine of x is bounded, it just wobbles along between -1 and 1, but the bottom's getting very big, so this is going to go to 0. So what do? We want to pinch this function sine x on x, and we simply use the fact that sine is less than 1 and bigger than -1. So sine x on x is less than 1 on x, and it's bigger than -1 on x. Now we've seen before, of course, that 1 on x goes to 0 as x goes to infinity, -1 on x goes to 0 as x goes to infinity. So since that is true, I just put some little arrows here showing that these go to 0. And I can just write down now that this limit then is 0 by the pinching theorem. So I should state what I'm doing here. So you've got to write some English down here by the pinching theorem. Okay, so that's that little example there. Now I want to come to a very special limit, and a very important one. It's one that you do at high school, in fact, and I want to prove this using the pinching theorem. It's a very special limit. We're going to look at the limit of sine x on x as x goes to 0. Now you can't just put 0 in, you get sine of 0 as 0 over 0. It doesn't make any sense. And you probably already know what this limit is, perhaps from high school, as x goes to 0, but this limit is very important when we come to differentiation, in fact. We need this fact to be able to differentiate sine of x. Now the proof of this is very lovely, and it's a really nice proof. There are various proofs of this. Some use arc length. I'm going to do it here by areas, which I think is actually the nicest way of doing it. And so here's my picture. So consider the diagram here. Now it's showing a sector of a circle. So this is part of a circle here. That's the center of the circle. This is a sector of a circle, and it's a unit circle. That means it's radius 1. So that length there is 1, and that's the radius of the circle is 1, radius of the sector. And it contains an angle theta down here that's in radians, of course. If we're going to be taking limits and things, we need to be in radians. And the angle is between 0 and 90 degrees. So I'll just take a little sector of a circle here. There it is. Now, at this point, I'm going to draw a tangent to the circle. So this will be at right angles. and I draw that up to here, and I'm going to extend this radius up until it meets this one to give me a triangle here. And I'm also going to drop a line down here to get another triangle here. So there's the picture, and let me mark in some of the information we've got. So we know this is theta, this is 1, this is 1. So we can use some basic trigonometry and say, well, this is the opposite over the hypotenuse. The hypotenuse is 1, and that's the sine of the angle. So this length here is sine the angle theta. And this is the adjacent over the hypotenuse. That's the cosine of the angle theta. That's in this triangle. Now in this big triangle here, this is the opposite over the adjacent, and the adjacent here is of length 1. Opposite over adjacent is the tangent of the angle. So all the three trig functions are there. There's the tan of theta up here. So I said here we can use trigonometry to mark in the various lengths as shown. And we're going to look at the area of, we're going to compare areas. So the area of a sector is a half r squared theta. That's a well-known formula from high school. Area of a sector, a half r squared theta. And r is the radius, which is 1. So that's going to be just a half theta. So we're now going to compare the various areas. We're going to compare the area of this triangle will be less than the area of this sector, which will be less than the area of the big triangle. So we're going to write down the three areas. This area of the triangle is less than the area of the sector, is less than the area of the big triangle. Now let's just write down what they are all going to be. Well, the area of this triangle is a half the base times the height, so that's a half cos theta times sine theta. The area of the sector is a half r squared theta, but r is 1, so that's a half theta. The area of the big triangle is a half the base, that's 1, times the height, so that's a half tan theta. So we get this lovely inequality connecting everything together. Now we've got a factor of 2, I'm going to get rid of that, multiply everything through by 2, and then I'm going to take reciprocals, which I must do very carefully, because when you take, everything by the way is positive. These are all positive here. So remember that from our very first week we mentioned that if you take reciprocals, you flip the inequality signs around. So that means the tan, 1 over tan, is going to end up at this end of the inequality. We're getting rid of the 2's. 1 over theta will still be in the middle, and this one will move to the other side of the inequality, because I'm taking reciprocals, and that flips all the inequality signs around. Well, tan, of course, is sine theta on cos theta, and so we'd like to get rid of the tan and get everything in terms of sines and coses. So I replace the tan theta with sine theta on cos theta, and 1 over that will be cos theta on sine theta. And so we arrive at that inequality. Cos theta on sine theta and is less than 1 on theta is less than 1 on sine theta cos theta. Now, unfortunately, I've got to go to the new page at this point, but you will have the notes in front of you, so you can just keep that there. And all I've done there is I have divided out, I've multiplied both sides by sine theta. Okay, so I'll just write in here what I've done. I've multiplied by sine theta, the previous inequality. Now sine theta is positive, there's no worries here because theta is between 0 and 90. And that lands me at this very nice inequality, because this is looking very much like what the limit we were looking at. So I'm going to replace the theta with an x now. So if x is between 0 and pi on 2, I can write down this inequality. So cos x is less than sin x on x is less than 1 on cos x, provided x is between 0 and pi on 2. Now we want to take limits, and I've got to worry about what happens. This only works if x is bigger than 0. But I want to take a limit as x goes to 0, so I've got to worry about what's happening on the other side. So if x is negative, then minus x then will be a positive number. And that means I can apply the inequality here. I just replace the x with minus x. Now cos is an even, so I get cos of minus x is less than sine minus x on minus x is less than 1 on cos minus x. Now the point is cos is an even function, so cos of minus x is the same as cos of x. And sine is an odd function, so if I've got sine of minus x, I can take the minus out, and that'll cancel with that minus, and I still get sine x on x, and again cos is an even function. In other words, this inequality holds whether x is bigger than naught or when x is less than naught. So either side of naught doesn't matter, you get the same inequality. Finally then, I'm now going to apply the pinching theorem. So we're going to see what happens as I let x go to 0. Well, of course, the cos of 0 is 1, so as x goes to naught, cos of x goes to 1. So if I take limits throughout here, this one goes to 1, this one goes to 1, and so by the pinching theorem, this limit exists and it equals 1. And there's our very important limit that sine x on x, that limit equals 1. And we'll have a look at a couple of quick examples of this. This again is sort of high school. You ask these sorts of limits in high school, but just to quickly remind you how it works here. So we're going to look at going to use this result to look at the limit as x goes to naught of sine 3x on x and tan x on x. So here's the worked solution for this. Okay, so we're looking at the limit as x goes to naught of sine 3x over x. So what do we do? Well, I really want these to be the same. So I've got sine of 3x and I want 3x down here. So you cheat and you put in 3x. You wanted to see sine 3x on 3x, so you put in 3. Now, of course, when you cheat, you're always found out. So before anyone looks, I'm going to put a 3 here to cancel out. And now I've got sine of 3x on 3x as x goes to 0. And that limit goes to 1. And don't forget, I've got the 3 out the front, so that limit is 3. Well, in part B, we're looking at the limit as x goes to naught of tan x on x. And we're going to use our important fact that tan of x is sine x on cos x. So I'm going to replace the tan with sine x on cos x. And I'm just going to rewrite it, keeping the x with the sine x. Now I'm really using now my algebra of limits that we mentioned just recently. The algebra of limits says if you've got the limit of the product of two functions is just the product of the limits. So I can use the algebra of limits to split this into 2 bits. So it's the limit as x goes to naught of sine x on x, limit as x goes to naught of 1 on cos x. And this limit we know is 1 because we just proved that. And as x goes to naught, cos of naught is 1, so this is going to 1, and 1 times 1 is 1. And so there is the limit. Now we're going to have a look at some other types of limits. So there are 2 other types of limits we need to consider. These are the so-called one-sided limits, where we approach the point from one direction only. Up till now we've been looking at limits that go from either side. So we're going to look at limits firstly from what's called above. So forget the epsilons and deltas business for the moment. What we're thinking about, we've got a function here, and we're approaching this point A from this side. So we're taking a limit as x goes to A, and the little plus there means from above, numbers that are bigger than A. And we're going to say that that equals L, and our epsilon delta definition this time is going to say, given epsilon bigger than naught, there is a real number delta, so that if x minus A is less than delta is bigger than naught. That is, this time we're only approaching it from this direction. So the x is going to be bigger than a. So we don't need absolute value signs here now. The x is bigger than a, but less than the width of my band. And if I take an x inside this band, then the f of x is inside the epsilon band. So for these right-hand limits, as they're called, we've still got our epsilon band both sides of the limit, because it could come in from this way as well. And what it says is now you have to tell me how big this band has to be, so that if I take any x to the right of a, and then I look at f of x, then that's going to be inside the epsilon band. Well, similarly, we can take limits from the other side, where x is less than a, in which case we're looking at a minus x, that'll be positive. And again, we have a similar epsilon delta definition here. We write this as x goes to a. We put a minus sign here to show that we're going from numbers a bit less than a, so we're going in this direction. And again, I tell you how wide the band is. You've got to tell me what the delta is, so that if I take any x in here, then the f of x is inside the epsilon band. Now we need these sorts of limits because we're going to look at a moment a limit like this one down here, and the square root of x, for example, is not defined for x negative. So if I'm going towards 0, I have to go from 0 to the right of 0, not from the left. That's why we need these special left and right limits. So we'll have a look at an example of one of these here, and bear with me while here we are, there's the word solution here. So we're going to prove from the definition, this epsilon delta definition, that the limit as x goes to 0 from above the square root of x is 0. Might just draw a little picture here before we look at the solution. So square root of x looks like this. And you see the function is only defined for x positive because it's a square root. So if I'm taking limits, I can only go from above. I can't go from below. I can only meaningfully talk about a right-hand limit. X goes to 0 from above. Now, happily, the details of this are actually not very difficult, as we'll see. And so I'll just go through one of these. So we're going to have an epsilon delta proof that the limit as x goes to 0 from above root x is 0. So again, it's probably worth drawing a picture again here. And we're looking at going towards this way. So my x is going to be here, and we're looking at building a little delta interval around here. So we quote the mantra again: given epsilon bigger than 0, put delta equal to I don't know yet. Then if x minus 0, that's this 0 here, so if x minus 0, if this length is less than delta, so this will be x plus delta here. No. So sorry, this width here is going to be of width delta. So if I'm within delta of the origin, if x minus 0 is less than delta, i.e. that's the same as 0 less than x less than delta, then I want the difference of this minus its limit. Well, that's just equal to the square root of x. Now x is less than delta, so I can say this is less than the square root of delta. And we wanted it less than epsilon, so I'm going to just put this equal to epsilon. And then before anyone looks, I square both sides of this. Delta is going to be epsilon squared. So if I draw a little band around here, an epsilon band around here, then my delta band has to be of width epsilon squared. And then if x is within delta of 0, the function is within epsilon of its limit 0. Now we'll have a look at some further examples of this in the tutorial projects. Now we come now to try and look at continuity, and we're going to firstly begin with continuity at a point, but I think we'll continue this one in the next recording.